Okay, so we're going to do Coulometry today, and then hopefully get into our electroanalytical techniques that are a little bit more substantial. But before we did that, I wanted to let people know that, one, I did move back that homework on chapter 15 a little bit. I will probably move back the homework on, well, there's no homework on this section. So I got a little bit extra time on that. I will be staying after class to answer some questions about the HPLC and the GCMS lab. The other big thing is, after looking through all of the responses to the survey about whether or not you want to do the exam face-to-face or online, we will be doing that face-to-face. I still have, oh, sorry, online. We will be doing that online. I have not decided whether or not I will let you have a note card or something. I'm kind of leaning in that direction, but not 100% on that. So we'll do it online. Note cards are a maybe. You know, I'll have to think about that, but you know, I'm leaning towards having note cards. Trying to think if there's any other super duper important or class businessy type of stuff that I need to go over. I don't think so. So yeah, without any further ado then, I guess we will go on to section 17-3, which is coulometry. So this is another one of our bulk techniques. Last time we've been talking about electrolytic cells. And electrolytic cells are cells that are basically run backwards, where we're putting electrical energy into a system to get it to do work for us, rather than looking at our galvanic cells, where we've got a chemical reaction and we either extract a potential and we get it to do work for us, or we look at a current. So here we're applying energy into a system, basically running our chemical reactions backwards. We're looking at the unfavored chemical reaction, sometimes called electrolysis. The cell setup is pretty similar, but we can do different things when we do this. Right? When we calculate the potentials that we need for it, we had a couple of other considerations, such as overpotential. So if you just looked at the table, and you'd say, okay, well, if I hook this cell up and I get 0.3 volts to run the reverse reaction, I'm going to need a little bit more than 0.3 volts to give it some overpotential, to get some electrons over that energy barrier. And then we've got what's called an IR drop, because we're trying to push things through a system. And we talked about weight and polarization. We talked about things that we can do to help minimize some of those. So we need a little bit more oomph going in the backwards direction than we do in the forwards direction. And now we're going to talk about, we talked about bulk electrolysis and gravimetry. So I'm going to deposit stuff onto an electrode surface, get the mass. That's going to tell me how much stuff I've got, and the potential at which things start to play out is going to be specific to different elements. So different chemical reactions have different potentials, and so when you reach that threshold potential, you'll start to deposit one material. You might need to go to a higher potential to deposit another. So coulometry is looking at how are we measuring the current or the charge that's going into our system, not so much the mass of the stuff that comes out on the other end. Okay, so charge measuring methods is what we're doing with coulometry. Electrogravimetry is kind of the opposite. We're looking at the other end of that process. So now we're looking at the front end, the charge that's going into it. And we get Q, which is our charge, is equal to the current times time. So charge is current times time. And that's really just going to bring us to Faraday's law, which says that the number of moles of analyte are going to be equal to the amount of charge divided by the number of electrons that are involved in the process, divided by Faraday's constant, which is coulombs per mole. So we can do a couple of different ones. One, we can different ways to do coulometry. One, we can control the potential. This is called potentiostatic. So sometimes you'll see an instrument called a potentiostat. Now, a potentiostat can refer to several different devices. Here it is referring to one that holds the potential steady. And then you can record the current as a function of time. And then you can integrate the area under the curve for that. You could also do a controlled current. So An example of that would be coulometric titration. So you're using electrons as a titrant, and the magnitude of the current is analogous to the molarity of the concentration. So your amps are going to be similar to what your concentration of your titrant was. And you're going to measure the moles of electrons going into the system, and then time takes the place of the volume, and you can still use an indicator. So like 110 phenanthroline is a good electrochemical indicator. And you use electrical measurements to determine the equivalence point. And you get a very similar looking curve, right? You're going to get a sigmoidal shaped curve, just like you would with a regular acid-base titration. And really, your acid-base titration that you're measuring with a pH meter, that's still an electrochemical measurement, but that's a voltage measurement rather than a current measurement. So coulometry, chemical analysis based on counting the electrons used in that reaction. And coulometric methods are based on measuring the number of electrons that participate in that chemical reaction. So if you got cyclohexene, you can titrate it with bromine, and you can generate it by electrolytic reduction or electrolytic oxidation of bromide. So you've got bromide floating around in solution. You throw in some electrons in there. The Br minus turns into Br2. The Br2 can attach itself to the cyclohexene and form trans 1,2-dibromocyclohexane. That's what a Markovnikov addition. My organic is not the best. So you just set up a cell that looks something like this, right? You've got a generator anode and a platinum cathode, and then some detector electrodes over here. And you've got a little magnetic stir bar, and you're going to put in some electrons, and you're going to stir up the solution. And as you put electrons in, you turn your Br minuses into Br2s. Your Br2s react with the cyclohexane. Right? The Br2 titrant is not delivered with the burette, rather you generate it on the spot. And it's carried out under a constant current. Now the titrant generating half reaction generates Br2. You take two bromines, you form bromide, two bromides, you form a bromine, and two electrons, that reacts with the cyclohexane. And the endpoint is detected as an increase in the current between the two platinum detector electrodes. The increased current requires the presence of both bromide and bromine, so bromine and bromide. This condition is only met after the equivalence point, because before that, all your Br2 is getting snarfled up and used by the cyclohexane. Right. So, for example, you got a 2 ml volume containing 0.63113 milligrams of cyclohexane per milliliter. You're going to titrate it like we did in the previous setup. How much time is required for a titration at a constant current of 4.285 milliamps? Right. So we've got our milligrams of cyclohexane. Right. We can convert that into moles. So our plan is we're going to convert that into moles. We've got our current, which is in milliamps. So that's going to be 1 amp is coulombs per second. We're going to figure out how many coulombs we're going to need. Right? And then we know that we're going through 4.82 millicoulombs per second. We can figure out how many seconds we need. So that's our general plan. Right? So the moles of cyclohexane, we're going to take our 2 milliliters, and we've got a volume and we've got a volume and concentration, and we've got milligrams on the top. We're going to use the molar mass. We're going to convert that into millimoles. In the reaction, 1 molecule of cyclohexane is going to take 1 molecule of Br, which requires 2 electrons. So our moles of cyclohexane are going to be equal to the current times the time divided by N times F. Right? We're going to rearrange to get time is equal to the millimoles of cyclohexane times the number of electrons times Faraday's constant divided by the current. So we get our time is 0.0488 times 10 to the minus 3 moles times 2. That's the number of electrons we need times Faraday's constant divided by the amps, and we end up with 595.1 seconds. So just about 10 minutes to reach that equivalence point. Right, so this is really just rearranging that Q is equal to I times T experiment, right? So Q is equal to IT. That's the important equation to remember. It is useful to partially isolate the counter electrode when a species generated at the counter electrode might interfere with the analysis. Right? So oftentimes you are going to undergo reactions that could either physically block or kinetically block access to your electrode surface. They could generate a species that would irreversibly bind to your electrode surface. There are lots of ways that you can get something that, or it could be something completely unintended, like the electrolysis of water. Right? You go past where your reaction is supposed to happen, right? You want to get it to go faster, so you crank the voltage up, but now you're starting to electrolyze water instead of undergoing the chemical reaction you're interested in. So there's lots of ways you can get things generated that you do not necessarily want. So here, you got the counter electrode isolated by a glass tube with a fritted bottom. Right? So you got this fritted bottom down here, and so this is going to kind of keep our counter electrode a little bit safer from any yucky stuff. Interference from gases formed at the counter electrode is prevented because these are going to bubble up and out of the cell in a way that's prevented from mixing with the bulk solution. That's where you're going to prevent some of the gas that might bubble up and mess with your solution by isolating it. So ions diffuse freely through the frit at the bottom of the tube. Right? So they're free to move through and maintain charge balance. Right? In constant current methods, like the bromine cyclohexane titration, are called coulometric titrations. If you know the current and the time, you know how many coulombs have been delivered. Controlled potential coulometry in a 3-electrode cell is more selective than constant current coulometry in a 2-electrode cell. That's because the working electrode potential is constant and the current decreases exponentially as the analyte is consumed. Right? So here you're keeping the voltage on that electrode the same, right? And you're letting the current change over time. Now, if our current is going to be charge per second and our potential is always the same, as we start to run out of stuff, right, our current and our ability to pass charge through is going to decrease, right? We just don't have enough gas in the tank for our car to keep going. Right? So we're going to keep that pedal to the metal, but we're going to start to slow down when we start running out of gas. So because the working electrode potential is constant, the current is going to decrease exponentially as our analyte is consumed. And so as we start running out of stuff, we don't have as much things there physically to have electrons hop onto or off of. And so our current, which is the movement of charge, is going to decrease as well. And so it's going to go fine, and then you're going to see, whoop, that's going to drop off. And this is very similar to why batteries, right, are going to maintain a fairly constant voltage until they start to go dead real fast. Okay? Charge is going to be measured by integrating the current over the time of the reaction. So here we've got Q is equal to the integral of the current as a function of time from 0 to whenever the reaction stops. So application for this would be measuring fructose concentrations in juice using a controlled potential coulometry in a 3-electrode cell. So if we got a reaction, if our reaction is the oxidation of sugar D-fructose, we're going to go from D-fructose to 5-keto D-fructose using D-fructose dehydrogenase. We start over here, we're looking at our current as a function of time. It starts off pretty high, and then it's going to drop off exponentially. If we measure the charge, which is the area under the curve, that's eventually going to flatten out. Right? So we're going to start off with a big peak over here, right? And this is going to give us the area that's going to give us our charge underneath the current. And because we're looking at coulometry, we're measuring our charges, it's this area that we're interested in. The reference electrode is silver chloride. Our working electrode is going to be a carbon electrode held at plus 0.5 volts versus that AgCl reference, and our auxiliary is platinum. Platinum's a really common auxiliary electrode. Our catalyst is going to be the enzyme D-fructose dehydrogenase, which is going to be coated onto that carbon electrode. So when they say coated onto that carbon electrode, I talked about Nafion before. So Nafion is this kind of interesting polymer that's good for being porous, and it's used in a lot of electrochemical applications. So sometimes all you do is you take some of that like bulk Nafion and you kind of stir it up with some of your enzyme, and you just kind of slather it on like a paste on top of that enzyme. So when they say coated on that enzyme, it could be like, you put a little drop on there. It could be like spread on. You might have it on like the spinny thing and spin coated on there. There's lots of ways you can get that on there. So amperometry is our next section. Amperometry, you measure the current between a pair of electrodes that are driving an electrolysis reaction. So one reactant is the intended analyte. We measure the current, and the analyte concentration is proportional to the measured current. And so our Clark oxygen electrode is an example of amperometric measurement. So the Clark oxygen electrode is used in medicine and biology to measure dissolved O2 by amperometry. So this is kind of the, not really the gold standard, but if they have to do a more extended blood oxygen analysis, this is probably what they're going to use. This is one of these Clark oxygen electrodes. So, you know, you can get some quicker ones using like the FETs. We talked about those when we were doing our potentiometric measurements. They would probably calibrate that against one of these Clark oxygen electrodes. Measures dissolved O2 by amperometry. I have a silicone rubber membrane right down at the bottom. That's permeable to the oxygen. The oxygen is going to diffuse into the electrode through the rubber and is reduced at the gold tip on the PT wire. So we've got a gold tip onto our platinum wire. So mostly platinum, a little bit of gold, probably then has a connection to a copper wire just because it's cheaper. The electrode contains a silver guard electrode, which is kept at a negative potential. And it's going to reduce O2 diffusing in from the top of the electrode so that it doesn't interfere with the measurement of O2 diffusing in from the sample, right? So this guy here, this AG guard electrode, is to stop any oxygen that might be coming down the other way through our electrode, because, you know, we work in kind of an oxygen-rich atmosphere. And so this guard electrode is just saying, okay, any oxygen that's trying to get down here, we're going to zap it with this one. So that the only oxygen that we're going to measure at this tip is coming up through this little rubber membrane. The Clark electrode itself is calibrated by placing it in solutions of known concentration, and you get a graph of current versus oxygen that you build up. Similar electrodes you can build for NO, carbon monoxide, NO2 minus. So these are the kind of electrodes that you can get them in kind of a big form if you're going to do like a bulk blood analysis, but these are also the ones that you can help miniaturize, right? So you can get these teeny tiny little electrodes. And I will have one of the, we will have a guest speaker come in and talk about like miniaturized electrodes at some point, either Thursday or maybe next Tuesday. So measuring the O2 on the brain of an anesthetized rat. So how are you going to measure something inside a brain? Well, you make a little teeny tiny needle and you make an electrode that is going to be one of these Clark electrodes, but on a very, very small scale. So you get a carbon fiber working microelectrode, and that's inserted into the brain of the rat. When the blood flow is cut off, O2 decreases by 93%. When your blood flow returns, and then you get more oxygen coming back in. Should be no surprise that you start to consume oxygen once your blood flow is cut off. So here you've got the current that you were measuring at your microelectrode. You cut off the blood flow, you change your current. Current's going to go down to basically zero. You let the blood flow go back on, and you see a return to baseline, but also a little bit of a bump as you end up over oxygenating it. And so this is what the surface of that electrode looks like. You've got a carbon nanotube that is supporting a little teeny tiny crystal of platinum, and then you got a big carbon fiber electrode. And so it's a platinized aligned carbon nanotube sheathed carbon fiber microelectrode for in vivo amperometric monitoring of oxygen. That's cool. It's just a fancy way of saying I can make this oxygen sensor happen on a very, very, very small scale with some kind of neat materials. One of the things that is interesting about nanotechnology in general is that for any chemical reaction to happen, molecules have to meet. So reactions happen at interfaces. And so surface area is really important. If you've got like, say a nail, right? It's the outside of the nail that's going to rust, and the inside of the nail is going to be relatively untouched and still pure iron. And that's because the oxygen and oxidation process can only happen at the surface, right, where those two things can meet. And so having these very, very, very small particles really increases the amount of available surface area. And so it kind of makes them a little bit more sensitive than something that would be just a completely smooth or planar electrode. And we talked about like those little stair steps, right? And like at the interfaces and at the corners, that's where all the interesting stuff was happening. Okay. So this is a type of biosensor, or the other one was, where we got a biological component such as enzymes, antibodies, or DNA that are going to give us some specificity to a particular analyte. Right? So rather than having just a membrane that is permeable to small plus charges for our H plus sensor, or a membrane that has a CO2 sensor where we've got, a reservoir of whatever it is we're looking for. Here we've got an embedded enzyme inside, and that embedded enzyme is doing some of the selectivity work for us. And so you can use enzymes and adapt them to lots of things. The ones based on electrochemistry or optical signals are really common, and examples of these biosensors include lactate sensors, hydrogen peroxide sensors, some breast cancer sensors, and blood glucose monitors, which is probably the most widely used type of biosensor. So here is how, if we don't have a note card, yes, I will give you ELF equations. Even if you have a note card, I would still give you the equations. So yes, that's a good question. Yeah, I mean the note card would be in addition to any equations. I will try to give you the equation sheet like a week or two before the exam, but really all I'm going to do is go through and like, here's an equation, here's an equation, here's an equation, here's an equation, and just give you all of the equations. Yeah. So people with diabetes monitor blood sugar or glucose several times a day to control the disease through diet and insulin injections. I have a soft spot for glucose monitoring because that was one of my projects that I worked on as a postdoc, and we were trying to do that with lasers and Raman spectroscopy for a continuous monitor rather than a finger prick test, because patient compliance on finger prick tests is pretty low because it's unpleasant. People don't want to do that. But this is what one of these test strips looks like. If you do not have diabetes or know somebody who's got one. So basically you prick your finger and then you put a little drop of blood onto the sensor surface, and breaking that down, it's really a miniature 3-electrode cell. You got 1, 2, 3 electrical contacts, right? And if you go over here, right, you've got a carbon working electrode, right, with glucose oxidized and a mediator, and usually that's like osmium. Right? You've got another contact that is going to be a reference electrode, and then you got a third contact, which is going to be your carbon working electrode coated with a mediator, but no enzyme. And then you got a hydrophilic mesh that wicks blood over the electrodes. That's a little drop of blood there. Blood then becomes the solution in which you have now dipped these 1, 2, 3 electrodes. And so blood and glucose will now be in between these 3 electrodes. And we've got a system that uses some similar strip type electrodes. We just have not done the lab for that this year because of COVID. So working electrode carries out an indirect amperometric measurement of glucose. You put a potential of 0.2 volts on the working electrode. This initiates the electrochemical oxidation of ferrocene, which if you are taking inorganic lab with me, we have made some ferrocene. So we've got some ferrocene. That's going to be the compound that they are undergoing the redox reaction for. So you're going to pick up an electron or give up an electron on the ferrocene. Well, the ferrocene is produced only when the glucose or an interferent is present. So you get glucose, and then you get some dimethyl ferrocenium cation. The glucose oxidase comes in, you get glucolactone and 2 of the 1,1 dimethyl ferrocenes. So you're going to convert these guys, and you get 2 H pluses. Right, on the other end, you've got a potential of 0.2 volts. So the ferrocene is produced at electrode 2 only when an interferent is present. Electrode 2 does not have the enzyme. And so those guys kind of serving as a control. Okay. So our glucose signal is going to be the signal of glucose plus the interference minus the signal from the interference. So the working electrode 1 signal minus working electrode number 2 signal is going to give you just the glucose signal. So it's kind of do a little bit of a background subtraction. So it's going to take away the extra current that's produced by the interferences. So amperometric measurement of the glucose produced by hydrogen peroxide is another way. So you got hydrogen peroxide is produced by reaction with glucose. You've got glucose and oxygen and glucose oxidase, and you're going to get glucosilactone and hydrogen peroxide. You put a potential of 0.6 volts applied to the working electrode, and that breaks down the hydrogen peroxide, H2O2 to O2, H plus, 2 H pluses and 2 electrons. This is measuring the glucose in millimolar versus the current in nanoamps. So it's not a lot of amps that you're looking at. You don't have a lot of stuff in solution, and you've got a relatively small surface area. So the amount of charge that you're actually passing is pretty small. This is a very optimistic curve for what the spread of this data looks like. This would be if you are doing it in a lab. This data looks a little sketchy to me in terms of the noise level. That noise level should be a little bit higher. They're doing this under very well controlled circumstances. They might be doing it as a sample standard addition, but real-time biological conditions, you're going to end up with a lot more variability in that data. This is basically how they used to do it. This is a very traditional method with the glucose oxidase and then measuring the peroxide. You've got a variable oxygen concentration, and you need a higher voltage. Replacing the peroxide with the ferrocenium with this guy as the mediator requires less voltage, and it doesn't have that oxygen dependence. Some of the better glucose sensors use osmium as a mediator instead. So rather than having like ferrocene, and so rather than doing the electrochemistry on the peroxide, which is the very traditional way, or the ferrocenium, they do it on osmium instead. And osmium's got a really nice electrochemical response. So melamine, this was in the news a couple years ago. So there was an issue with people putting melamine in milk in China, and they also had a thing where they were trying to up the measured protein content by adding stuff to like pet food. And I can't remember what they were adding to the pet food, but it was basically they were upping the nitrogen content. And so when they did the analysis for the protein analysis was like, well, how much nitrogen you got in there? And they were like, we're just going to throw in some random crap with nitrogen. That's really bad for you. So melamine is a poisonous nitrogen compound that was deliberately added to milk for babies that have been illegally diluted to mask the fact that they were diluting it. The glucose meter is employed in one of the methods developed since 2008 to measure the melamine in milk. When melamine from a milk sample binds to the colored aptamer, 2 DNA fragments are liberated from the aptamer. 1 fragment is attached to the enzyme invertase, which can convert sucrose to glucose. That's measured with the home glucose meter. The observed amount of glucose is related to the amount of melamine in the milk. And so an aptamer is just a short strand of single-stranded DNA that's going to have a match to a complementary amount, to a complementary set of base pairs. One's going to be attached to a magnetic bead, right? And the other one is going to be attached to this invertase molecule, right? So our aptamer is basically holding these 2 things together. You can then take the aptamer and bind it to the melamine. The invertase then cleaves the sucrose to make glucose. Once you've got glucose, you can measure that with a glucose meter. Demand for glucose monitors stimulates growth research targeted at improved performance. Yeah, I got paid to do that. Monitoring reaction by coulometry instead of amperometry. Using a different enzyme to catalyze glucose reaction. Electrical wiring to increase the rate of reaction, prevent reactants from diffusing away from the working electrode. Coulometric measurement is independent of the temperature and is insensitive to the activity of the enzyme, because your enzyme activity is going to be temperature dependent too. And the mobility of the mediator. So how can that ferrocene migrate through that little electrode surface and get to the surface of, go through that little electrode cell that you made and get to the electrode surface. Current is affected by the depletion of glucose during measurement, right? So you saw in that one measurement where your concentration drastically affects your available current. Okay. So finding better ways for enzymes and cofactors. So glucose monitor performance can be improved by replacing the enzyme glucose oxidase with glucose dehydrogenase. So your cofactor of R2 with PQQ, which is pyrrolylquinone. Right, so you can take your glucose and your PQQ, and you're going to get gluconolactone and PQQH2. The concentration of the PQQ is easier to control than the concentration of O2, because this guy is going to be aqueous and this guy is going to be gas. Glucose monitor performance can be improved by connecting the enzyme to the electrode, right? So kind of hardwiring that enzyme straight on it via a mediator transporting polymer network, right? So kind of embed this guy in a polymer. So embedding things in polymers. I was talking to my friend about just that last night, because we were playing some video games, and we're talking about Nintendo Switch cartridges and how they're really, really small. And they did not want you to eat the Nintendo Switch cartridges, so they put a bittering agent in there. And that bittering agent in the Switch cartridges, if you ever get a hold of one, tastes pretty terrible. But it is actually bound directly onto the polymer. So the flavor will never go away. It's not like it's mixed into the polymer like a plasticizer is, and then it'll diffuse out over time. It's not, the polymer is like a big ball of spaghetti, right? And then, you know, sometimes they'll put in things like a colorant, or they'll put in a plasticizer, and those are things like sauce on the spaghetti. The way that the Switch has done it is they have actually changed the spaghetti structure itself, right? The noodle, to have that molecule as part of the backbone, so that the flavor will never go away, which is the idea of making deliberately flavored plastics. I think is kind of cool. But you don't have to do it with plastics. You can do it with something like glucose dehydrogenase instead, right? And then now you've got your glucose dehydrogenase not kind of just floating around in your big bowl of polymer spaghetti, but it's going to be directly bound to it and then bound to that electrode. So it's not going anywhere. It's going to be held a little bit more closer. It's not as free to diffuse. And then there's some of those osmium ligands that are on there. So you got improved wiring. Okay. Section 17.5 is voltammetry. Bitrex is nasty as hell, can confirm. Yes. Make a gum like that so it never loses flavor. Everlasting gobstoppers. There you go. I think you guys have a potential market there. Just cut me in for a piece of the action. All right, so section 17-5 is voltammetry. And honestly, this is if you're going to be doing like hardcore analytical electrochemistry, electroanalytical techniques in a research lab, chances are pretty good, maybe 70% good, that you're probably going to be doing some sort of voltammetry. You will see these things called cyclic voltammograms all the time, just because it is a technique that gives us a lot of information. So this is not something that you would necessarily see in an industrial application very much. You're going to see in industry, yeah, maybe some electrogravimetry. Honestly, nobody's going to do that anymore. You might see some coulometry. Yeah, you're going to see definitely things like your glucose sensor showing up places. But those are going to be very applied engineering, out in the real world type of measurements. Voltammetry, like the kind we're going to talk about, are going to be, I want to investigate how electrons work in a chemical system. I want to see how many electrons are involved in a process. I want to know what is happening with some unique molecule. So the very academic, more fundamental stuff that we'll see is going to involve a lot of voltammetric techniques. So voltammetry is confusing because you're going to measure current with respect to voltage, and you're not measuring voltage. Potentiometry is the one where you're measuring voltage. So it kind of developed in the 1920s out of a technique called polarography. And we got a couple of different flavors of the voltammetry that we can do. You can do stripping voltammetry, polarography. Polarography is defined by its use of the dropping mercury electrode, the DME. There's a technique called differential pulse polarography that's probably the most used now. Then you've got regular voltammetry, which breaks down into linear sweep voltammetry, cyclic voltammetry, which is by far the most common, and square wave voltammetry, and then you've got amperometry. And that's Yaroslav Erosk, and he was the guy who invented polarography, which is funny because he's not a Pole, he's a Czech. There's a lot of Czechs that are involved in analytical chemistry stuff too. So why do we care? Well, stripping voltammetry is highly sensitive, parts per billion level for trace elemental detection. So you could do the guess which toy has too much lead today experiment. Polarography, they use that a lot in pharmaceutical analysis. Not as much as they used to, but it's still a pretty common technique. The reason being that it works well in aqueous solution, and it's going to give you some very specific information about stuff. And then voltammetry, you can use it in a chromatography detector. You can use it in analysis of electron transfer mechanisms. So, you know, those arrows in organic chemistry, right? Yeah, voltammetry is what you'd want to use for that. You can look at absorption or kinetics or physical processes. So this is a lot of the fundamental academic-y type of stuff. Amperometry, like we saw, was a lot to do with actual sensors and monitoring things. So voltammetry is a collection of methods in which the relation between current and voltage is observed during an electrochemical process. Current from an oxidation or reduction is measured as the potential of the working electrode is changed. Right? So when we did that amperometry, we kept the potential steady, right? Or we kept the current steady and we're like, yeah, we kind of don't care what happens with the voltage. Here, we are not only we're keeping the voltage under our control, but we're systematically changing it, right? So we've got our little voltage knob and we're going to go, and we're going to change it, okay? And then we're going to look at the current as the thing we are measuring. So our voltage is going to act like our independent variable, and our current will be the dependent variable. So the current versus potential graph is known as what's called a Voltammogram. Okay? Different techniques come from different voltage patterns, right? So you could just take that knob and you can go whoop and go from low voltage to high voltage, or from high voltage to low voltage. That's called a linear scan. If you are going to put in a triangle wave, that's going to be cyclic voltammetry. So you're going to take the knob and you're going to go whoop, whoop, and you're going to go up and down and up and down. If you have a kind of combination of those two, right, you could do square wave voltammetry, where you're going, keeping it one voltage, jumping it up real fast, like dropping it down for a little bit, and up and then down and up and down. You're going to put a square wave onto this sweep. Or you could do differential pulse. That's a differential polarography is you're now putting that on putting like kind of a square wave on there, but rather than being flat and holding the voltage constant for a while, you're letting it still ramp up. That's so you're still doing differentiating your pulse and going back and forth a little bit. So this is what this schematically looks like. So you've got a 3-electrode cell, like we saw before. We have a working electrode, and that's our business end. We have a reference electrode, and then we've got our counter electrode. Okay? And so we're going to measure the current that is passing between the working electrode and the counter electrode. So we're going to measure through this. And then we're going to apply a potential, a controlled potential between the reference electrode and the working electrode. So we systematically control this part, and we watch to see what happens as the electrons flow through this part. Okay. So you're going to sweep, for example, at 2 to 5 millivolts per second. That means you're going to turn, how fast are you turning that knob? Right? So our analyte is going to be either oxidized or reduced at that working electrode. Our reference electrode is going to be something like a SHE or an SCE or a calomel electrode or an AgCl electrode. And our current is the thing that we're going to measure between the counter and the working electrode. Right? And oftentimes these counter electrodes are going to be platinum again. Right? So we're going to have like a little platinum wire. We'll have a reference electrode that's probably going to be AgCl. And then our working electrode can be a variety of different materials. So we got, this is our reference electrode. Right? Sorry, this isn't brain fart. This is an example of what some of those electrodes can look like. The simplest ones are going to be just like the ones we had for our potentiometry, are very, very simple. We're going to take a copper wire and stick it into a copper sulfate solution. It's going to be a Teflon body with a little disc of whatever material it is down at the bottom. And then we'll have a wire coming out. And then our electrode surface is right here. So you got to polish that guy up a little bit to get that surface nice and clean. The other kind that they're going to use in polarography is this dropping mercury electrode. So imagine a basically like a capillary tube. And you got a little reservoir of mercury in here. And then at the very bottom, you've got this little bead of mercury that's going to form. And that is your electrode surface. Okay. And when we talk about polarography, I will tell you why this is a gigantic pain in the butt to work with. There are pros and cons, but from my point of view, a lot more cons than pros. And so most of the time, you're going to be looking at something like one of these guys. So let's look at linear sweep voltammetry first. So in linear sweep voltammetry, what we're going to do is we're going to start off at 0, and then we're going to turn the voltage knob. Right, our voltage, we're going to apply, we're going to make our voltage between our working and our reference electrode. We're going to sweep that slowly from 0, and then we're going to make it a little bit negative. Right, nothing's going to happen. We're going to make it a little bit more negative, nothing's going to happen. We're going to make it a little bit more negative, and all of a sudden we start to see current flow. So this is the reduction of reagent A into product P. So nothing's going to happen for a while until we reach the point when that reaction can happen. Right? So now that we've reached the point where we can shove those electrons onto our reagent and we're going to form some sort of product, right? We need to reach whatever that we've got to get to that reaction potential, to the reduction potential, and a little bit more for our over potential. Right? So we're not going to see anything happening if we don't have enough oomph. Right? We don't have enough potential. Once we reach this potential, we're going to start to see current flow. At the midpoint here, right, this is going to be called E1/2. That's going to be directly related to what the reduction potential is for this reaction. So A going to P, right, A being reduced into P, that E1/2 would be pretty much the same value you're going to find on that charge. Right? So you're going to see a different curve for different things, right? So as you're going to sweep this voltage, you're getting more and more negative. You're going to start to see current happening, like, oh, I've reached a point where I can get some electrons flowing. All right, and then you're going to reach what's called a limiting current, where even though I'm putting in more potential, I just can't get more stuff happening, right? I've reached either a kinetic limit where I can't get electrons to get on there fast enough, or I can't get new A in, or I can't get new product in, or I can't get new reactants in, or I can't get new products out fast enough, so I can't refresh my surface. I'm going to reach some maximum limit. Right? So as your potential, right, goes up, or in this case, it's down and down and down and down and down, your current is going to form this kind of S-shaped sigmoidal curve, right? And the important pieces of information you get out of this are E1/2, which is going to be related to what's the electrochemical reduction potential of this reaction, of this half reaction. And then you're also going to figure out what I1/2 is. And you're going to get some sort of limiting current. And that limiting current is going to be proportional to what your concentration of your reactant is. If you've got more reactant, this curve becomes higher. Right? So you're going to get more reactant, it's going to go up higher. If you got less reactant, it's going to be lower. Your E1/2 is still going to be in the same place. Right? So it kind of looks a little bit like a titration curve, but we're going to pretend that it doesn't. Like, titrations are icky. Right? So our limiting current is going to be proportional to A times K. So could you make a standard curve where you've got a series of these things, right, of known concentration, and then you measure something and you're like, okay, well, now I know what K is. I can throw in an unknown, figure out where its limiting current is, and then figure out the concentration of A? Sure, you could definitely do that. Right? So if I gave you like 1, 2, 3 curves, and I told you what the concentration was, and then said, oh, here is the current, limiting current for an unknown, yeah, all you'd have to do is make yourself a nice little standard curve. Right? So these are useful for quantitative stuff. It's a little bit overkill, but you can do it. Right? So you get this sigmoidal voltammetric wave. And it's called a wave because it kind of looks like. Right? You've got your half wave potential, E1/2. Now the half wave potential is related and close to the E0 values for the half reaction, and that can be useful in identifying what you've got. So you've got your limiting current, which could potentially tell you something about how much you've got. And then you've got your E1/2, which could be potentially useful about identifying what you're looking at. So you've got 2 analytical questions, right? How much do I have and what is it? And this can be a useful technique for both. There are some variations on this, like hydrodynamic voltammetry, which is going to overcome the limit of mass transport to the electrode. So when you get this limiting current, one of the things that is going to limit the current is, can you get enough of your reactant to that surface to undergo a reaction? And so at the surface, you're going to start to stagnate and get a fairly stable concentration. Well, you can overcome some of that. Remember, we talked about polarization and stirring your solution. Well, one of the things you can do in this voltammetry experiment is to rotate the electrode or stir the solution. In polarography, they overcome that limit by using this mercury drop. Right? And so your drop actually drops off and you form a new electrode surface. You're actually regenerating your electrode. You can do what's called a fast scan, and you deliberately ramp the voltage up quickly so that the area around the electrode is depleted of the analyte. So you're deliberately going to pull everything out with a fast scan. Right? So looking at hydrodynamic voltammetry, you have this electrode surface, right? That's your little chunk of metal. Right, you've got this volt flow in the solution. Right at the electrode surface, you've got a laminar flow region. So it's going to flow smoothly at this surface, and then close to the surface. And then you've got a diffusion layer where it's basically stagnant solution. Right? And it's going to be we're going to give it this little symbol delta here. So this Nernstian diffusion layer is the important part because you got to get your stuff on the electrode surface. Right? Your reactant has to go from the bulk into this laminar flow region and then diffuse onto that surface. Right? And you can shrink the size of this diffusion layer in a couple of different ways. Right? So our equation for that Voltammogram, so we've got that sigmoidal curve, right? It's predictable, right? It's describable with words, and it's also describable with numbers. So the limiting current is related to the concentration, D, the diffusion, so how quickly things can move from the solution onto the electrode surface, how big the surface area is. Right? So if I've got more stuff, I'm going to get more things on the surface. If those things can move to the surface faster, I can get more current. If I've got a big surface area, I can get more. I've got more sites and more places where I can get charge happening, and it's related to the bulk concentration. And so our current, our limiting current, is going to be equal to n, the number of electrons, times Faraday's constant, times the area, times the diffusion, how fast are they going, divided by the change in concentration, times the change in concentration. And so all of these guys, n is going to be constant, Faraday's constant is a constant, it's in the name. The area should be constant, right? So you're not changing the size of your electrode as you're going along. The size of that diffusion, the little delta D in the diffusion layer is going to be constant. And so the only thing that's going to change is going to be our concentration. So that's where we're getting this I is equal to some K times C back in this guy, right? So our limiting current is K times the concentration. Well, that K is actually predictable. It's going to tell us about the diffusion and the surface area and how big that change in concentration is. After a lot of math, our Voltammogram can be described by this equation where our applied potential is going to be equal to our E1 half minus 0.0592 over N. That looks really familiar, doesn't it? Log times the current, log of the current at a given time divided by the limiting current minus the current at that time, which bears more than a passing resemblance to the Nernst equation you're already familiar with. If we assume that our K, A, is going to be equal to Kp, then we can say that our E1 half is going to be our E naught minus E reference. Right, so really our E1 half that we're seeing here is the same thing as our E naught, only adjusted by whatever our reference electrode's potential is. Right, so this is a good way for us to measure what's the E naught for our reaction. Do I know what the voltage is on my reference electrode? Yeah, that's why you're using it as a reference electrode. Can I then figure out what the E1 half is, and then from there figure out E naught? Yeah, that's exactly what you're going to do. So applications are going to be in voltammetric detectors for HPLC. So the rate at which you can do some of these scans is pretty fast. So like maybe a couple of seconds. So well within the ability for you to capture that as something that's coming off of an HPLC. In an industrial flow stream, that's another place where you can see these. So you can implant a little electrode surface and kind of run a scan every once in a while and get information about what's coming through a wastewater stream. And we already saw the amperometric sensors like the Clark oxygen sensors and the titrations we can do with those. So our rotating disc electrode is a way for us to kind of overcome some of the stagnation that happens at the surface of those electrodes. So a molecule, it's got three ways to reach that surface of the electrode. Diffusion, through that concentration gradient. Convection, in which the movement of the bulk fluid by a physical means such as stirring or boiling. And migration, which is the attraction or repulsion by a charged surface. Right? So it's kind of a complicated process. Right? How quickly can you get your analyte molecule to the electrode surface? Well, that's going to affect really the local concentration, which is going to then affect the amount of charge you can put through that system. Right? If you don't have any analyte at the surface, there's nothing there for that electron to hop onto. So you got to get your stuff there. You got to get your analyte there. It can diffuse. You can kind of push it there physically, or you can kind of attract it through electrostatics. And so that rotating disc electrode is fairly common. Working electrode for voltammetry, it's going to spin really, really fast, and it's going to give you a vortex that rapidly brings the analyte near to the electrode by convection. The analyte must traverse that final short distance by diffusion alone. All right, so it's basically stirring that solution kind of for you. You've got a polished electrode surface, and basically you've got a liquid flow pattern that's going to come up, right, and it's going to go off to the side. You've got the electrode tip, and basically this sucker just spins. It's spinning like rims on it. when I was in Georgia, there was a place down the street from me that literally lets you rent rims. Because, you know, if you're hoopty and you blew all your money on the car, but you still want some rims and you don't want to spend the money for rims, you can rent them rims. So yes, it was a rim rental place. I've lived in some classy places. So yes, basically you're gonna spin this guy. Rotating disc electrodes generally are more expensive because obviously you've got moving parts. They tend to break down. You will see the current be proportional to the rate of diffusion. So the faster you spin them, the more stuff you get to the surface, right? Because you're increasing the rate of convection. No, it wasn't rim time. It was rent a wheel. I did not hear the rim time. I did not hear the rim time radio jingle, which now I am. Oh God, I'm gonna have to look that up after I'm done talking to people. I'll write that down. Rim time radio jingle. So Voltammograms for oxidation and reduction of iron cyanide. So we got a limiting current, the oxidation, as observed at potentials above 0.5 volts. Right? So here we've got 0.5 volts, right? So once we go to plus 0.5 volts, we're going to hit our limiting current, right? We're going to have our E1 half, and then things are going to taper off, right? Our E1 half is always happening at the same spot. Right? Below 0 volts, there's a lower plateau where that's the limiting reduction of going the opposite way from the iron 3+ to the iron 2+. And what we're seeing here is that as we increase the concentration, we get a larger limiting current. We can make ourselves a nice little standard curve where we're correlating what's our limiting current versus our concentration of the potassium ferricyanide. Choosing the right electrode material is important. So platinum and gold electrodes are suitable for oxidation. So at negative potentials, water is reduced to OH- on a platinum and gold surface, which limits their utility for reductions. So platinum is actually a really good catalytic surface for electrolysis of water. So that at really negative potentials, you're going to generate hydroxide. So yeah, you can't do it so much for reductions, but for oxidations, it's great. Carbon electrodes are going to work great for both oxidation or reduction. Glassy carbon electrodes are called vitreous carbon. There is also pyrolytic carbon. So basically, it's a hard, brittle, kind of glass-like looking appearance. You heat your carbon under an inert atmosphere, and you end up with like this very hard, chunky, brittle. It's mostly disorganized, right? So it doesn't have that nice graphite-like hexagonal order to it. It's a lot more random and like here's a carbon, here's a carbon, here's a carbon over here. So you've got a mixture of sp3 and sp2 hybridization going on with it. Yeah, and it's difficult to get that to be reproducible because it's glassy, but it is not a glass. So it's a disordered solid phase material, but it doesn't undergo a glass transition. So you can't really like melt it and then reshape it like you would a true glass. You can boron dope diamond electrodes. Those guys are horrendously expensive, but basically you take a diamond and you're going to vapor phase deposit carbon. And so I will find a vapor phase deposit. So back in olden days, in the 1960s, when they first started making synthetic diamonds, they did it in analogy to the way that diamonds are made naturally, which is under immense heat and pressure, right? So the diamonds that we form, that are formed naturally, you know, they're formed in these kimberlite mines in, like there's a bunch in South Africa. So basically carbon, lots of heat, lots of pressure. If you look at the phase diagram for carbon, way up in the high PT range, the preferred form as that sp3 hybridized diamond form. Under standard temperature and pressure, it's graphite. So carbon was pressed and squeezed and heated and turned into diamond over millions of years. And then we dug it up, and the kinetic interconversion process to graphite is just really slow. So diamonds are not forever, alas. They are not thermodynamically stable at STP, but that kinetic process is really slow. And so when they first made the synthetic diamonds, they're like, okay, we're going to take some carbon and we're going to, you know, squish it and heat it, and boom, we're going to make a diamond. And that works actually pretty well because it's easy for us to make you know, pretty crude diamonds, and actually not pretty crude, some bulk diamonds with high temperature and pressure processes. In about the late 90s, 98-ish or so, they developed methods of growing diamonds layer by layer. So putting down a layer of carbon, and then you would basically flow through a gas that had carbon in it, and then it would start to organize itself on that surface into that characteristic diamond structure. And so you would deposit one carbon layer at a time. Now, the material that they used for making these most effectively was gas phase ethanol. And they found that tequila actually was the preferred gas phase deposition liquid. So they would take tequila and basically vaporize it and use this under this low pressure vapor deposition way. And so, but you can throw in some boron, and then that's going to act like a semiconductor. So like we saw before with our silicon, right? So carbon and silicon right next to each other vertically on that periodic table. So they're going to behave similarly. So using a boron doped diamond, it's very inert chemically. You can buy some. They are going to have a really big potential window because diamond doesn't really react with much of anything. It's got a very low background current, resistance to surface oxidation, high over potential for O2 oxidation, and they're visible, which is kind of neat. So you can actually like do a spectroscopic experiment on one of these diamond electrode surfaces. So, you know, we've got conductive glass, that's ITO, indium tin oxide doped glass, and that is conductive. If you are looking at a computer screen right now, you are probably using some ITO glass. You can do the same thing, but instead of doping glass, you're doping diamonds instead, and which is kind of cool because then you can do electrochemical experiments and spectroscopy experiments on the same surface. You've got different potential ranges you can work for or through. Platinum, you can work between -0.2 and 0.9 volts. Gold's going to go out a little bit further, 0.3 to 1.4, -0.3 to 1.4. Mercury is going to go a little bit more negative, -1.3 volts to 0.1 volts. Glassy carbon, nice compromise there, -0.8 to 1.1. Boron doped diamond, -1.5 to +1.7, and then a fluorinated boron doped diamond, all the way down to -2.5, all the way up to +2.5. So, you know, it's not a very exciting picture of an SEM there, but those diamond electrodes are horribly expensive. So I just bought a platinum electrode, and those guys cost about $300 for a platinum or a gold electrode. Glassy carbon is going to be a little bit cheaper. You're looking at maybe $200. I have not priced these recently just because the last time I looked at one, I was like, God, how much? And was like, no. So those are our electrodes. We looked at what happens if we just do this one wave. Let me just go with our single controlled potential, right? We're going to either go low and go high, or we're going to go high and go low. Cyclic voltammetry is going to do it's going to go up, and then it's going to go back down again. So it's going to reverse our potential profile. So we're going to have a forward scan, and then what's called a reverse scan. So we saw in our first set of slides what happens if we just look at either a forward or a reverse scan. We said, okay, we're going to end up with this kind of sigmoidal wave shape, right? Well, you're going to end up with something similar. It's just that now you're going to look at the reverse process as well. So you're going to ramp up our voltage, and then we're going to switch it and start going down instead. And you can come up with several combinations for these where it's like, it's going to go up, it's going to start at 0, and it's going to go up, and then it's going to go down to 0, and then it's going to go negative, and then back up again. Or you could like go start off in 0, and then go down, and then go up. You got a couple of, there's only so many ways you can mess with a triangle, right? So the point is, it's got an up part and it's got a down part. Right? Whichever one comes first, you're still going to end up with one of these waves, wavy looking things, except now instead of just having one wave, you're going to have two waves. Okay? So, and one of the confusing things about how these things are drawn, so you're going to end up with, here is our potential profile, and then you're going to end up with this guy, which is called a cyclic voltammogram. Sometimes these guys are called ducks because they look like little duck heads. But when I did this and I first learned cyclic voltammetry, I was doing a study abroad, and in Europe it is backwards. So I will mess up for you, and I'm letting you know now. I will do my best to keep it American style, where we're talking about the cathodic wave being on the top and the anodic wave on the bottom, but in Europe it's backwards. All right, so if I mess up, feel free to call me out on that, okay? Thank you for the 10-minute warning. All right, so in our cyclic voltammetry, we've got a triangular wave, right, at that working electrode. So not just whoop, we're gonna whoop, whoop. As the potential is swept forwards and then backwards, the current between the working and the auxiliary electrodes is monitored, and the reduction or oxidation currents, right, because we're going to flow electrons one way as we're going up, and then we're going to reach here, and we're going to flow the electrons back. We can flow the electrons back the other way. And so we've got an oxidation wave and a reduction wave. Right? And you end up with something that's going to look like this. Right? There's our kind of, you got to use your imagination. There's our duck shape, and there's the little beak, right? Where you're going to have a wave, right? And it's going to have a peak current, right? For both a cathodic and an anodic wave. So you got an anodic wave going this way and a cathodic wave going this way. And if you have a nice symmetrical looking shape, that means you've got a nice reversible chemical reaction. If you get something that looks like it was a duck that was hit by a semi truck and is now flattened, this is indicating that it's an irreversible reaction, right? I've got my cathodic wave happening, and then I don't reverse my things exactly the same way. Right? So it's got a different path that it's going back. You have a, let's see what else you have on here. You've got a peak voltage for your cathodic and a peak voltage for your anodic wave. You've got an E1 half that is happening halfway in between your cathodic peak and your anodic peak, and that's your E1 half, just like you would see with the E1 half on just the single wave. Okay. So let's take a look at what is happening. All right, so as we are sweeping our potential, right, we're going up, and at the beginning, we've got nothing that's happening. And then we're going to start to, once we reach point C, point B, we're going to start to have current flow. Right, we're going to reach our midpoint. We're eventually going to reach a peak current, but then at that surface, we're going to start to deplete the locally available analyte, right? So we're going to reach some peak current, right? We started to oxidize or reduce everything, right? So we started to reduce as much stuff as in there. And now at our electrode surface, we don't have available stuff, right? We have used up and we've reached our peak current, and now we're starting to consume our analyte or our reactant. And as our analyte or our reactant concentration decreases, our current is going to decrease. And it's going to kind of decrease and kind of fade out, right? But then here at point F, right, once we reach point F, boom, that is our switching voltage. Right? And now we're going to start bringing our voltage back down the other way. And so our reactants, right, we've depleted all of our reactants, so we've got a lot of products there. And so now we're converting our products back into reactants, and current is going to start to flow again, right? And it's going to reach some sort of peak, right? Until we've started to deplete our products, and then it's going to level out again, and we're going to come back over here. Right? So we got our nice little duck. Here's our beak, right? There's the feet. And this is a very typical shape for what our cyclic voltammogram is going to look like. So this is a nice reversible reaction. You get something like that, you can go, yeah, I got a nice reversible reaction. Right? We've got a peak current for our cathodic wave, and we got a peak current for our anodic wave. We know what the voltage is, right? Our x coordinate down here on this guy is important. Our x coordinate over here, our potential for this peak is important, right? Because halfway in between them, that's our E1 half. And our E1 half, we said, is that is E naught adjusted for whatever our reference electrode is. So here, our cathodic current, we're taking our iron cyanide or ferricyanide compound, and we're putting an electron on it, and we're going from a 3 to a 4. Right? Here, this little bump here at A is oxidation of water to give oxygen. Right? We're gonna have nothing happening, then we're gonna get current flowing. All right, up here, concentration starts to run out. Right, it's gonna run out and go slower and slower and slower. We're gonna get fewer charges. We're gonna switch our voltage direction. Now we're gonna do our anodic current. We're taking our 4- form and we're converting it into our 3- form. So, we're gonna get some current flowing again. And then we're gonna reach a peak down here. And then we're gonna be able to stop. We're not gonna have as much of our product that we're gonna consume, and that's gonna flatten out. Yep. So our EPA and our EPC, those are our peak potentials. Our IPAs are delicious and hoppy, and our IPC are going to be our peak currents. And for a reversible reaction, delta P, our difference between the peak current for the anodic wave and the peak current for the cathodic wave, is going to be 0.059 over N. Right? So the more electrons that are involved in this process, the closer and closer and closer and closer those two peaks are to each other. The shape of this curve is defined by what's called the Randall-Sevick equation, which says that our current is going to be 2.696 times 10 to the 5 times the number of electrons, the 3 halves, times the concentration, times the surface area, so how big of our electrode it is, times our diffusion, constant to the 1/2, times how quickly are we changing our thing, how quickly are we sweeping it. Okay? And so I will stop here and see if anybody's got any questions. This is a little bit trickier stuff. Really, the important stuff to know is going to be with this EPC, right? Knowing what those values are and what your current is, and can you do something with this Randall-Sevick equation? Okay. That's a lot to take in. So this is one where you probably want to review at least the cyclic voltammetry stuff. Honestly, I think the coulometry stuff is pretty straightforward. Q equals IG, how much charge you would put in. So not too bad. The cyclic voltammetry stuff, bring yourself back to that initial single sweep, and then it'll make more sense. You got a single sweep in one direction and then just a single sweep in the opposite. All right. Nobody else have questions? You can always just hit me up for office hours. I'm going to stop this, and then I'm going to open up the windows for office hours so that, no, can I do that? I'll just stop this one. I'll stop sharing, I'll stop recording. We'll do some real quick office hours because some people needed to or wanted to stick around and ask questions about lab. So you are more than welcome to stay, but I'm going to stop recording, okay? more